Hi, I'm Daniel Green. Today I'm going to tell you about soft disorder effective theory. This is based on a paper with Tim Cohen that appeared in July. So the plan for the talk is first I'm going to introduce the problem of describing the universe on the largest possible scales. I'll describe soft disorder effective theory and how it addresses this problem and apply it to quantum fields in a fixed de Sitter background and metric fluctuations during inflation. So describing the quantum mechanical universe on largest possible scales is one of the great outstanding problems in cosmology. It has to do with questions like, what is eternal inflation, and is de Sitter space fundamentally unstable? It also has more practical origins, like what should a theory of quantum de Sitter even compute? And the fact that we can't answer any of these questions might maybe suggest that we're not thinking about this the right way, or even that these aren't even the right, that we shouldn't even have to solve these kinds of problems, and maybe there's some kind of metaphysics problem. When we look at observations of the cosmic microwave background or large scale structure, we are seeing modes that evolved on Superhorizon scales. This is critical to our understanding of inflation, the need for it, and how it solves the horizon problem. But when we think about even basic questions about perturbation theory for these long wavelength modes, we encounter all kinds of problems when we move beyond tree level. So loop calculations are notoriously difficult to regulate. They also don't have any obvious power counting scheme, so that it's not obvious before one tries to do a calculation what the size of the contribution is expected to be. And the fact that these two problems are ultimately the source of a lot of confusion and disagreement in the literature about what loop corrections can and can't do in de Sitter space. A simple example is the conservation of the adiabatic mode zeta. This has long been known to be conserved on Superhorizon scales classically. More recently, it's been proven to all loop orders, so that as some kind of operator statement, we know that the correlation functions freeze when all the modes are Superhorizon. But even in these cases where we think we understand the answer and can derive it, these proofs involve complicated diagrammatic arguments. And it doesn't capture this apparent simplicity of the statement and ultimately gets tied into these technical problems. So what is the actual problem? Well, in most cases, the basic issue is that at some stage of a loop calculation, one encounters a divergence that's not regulated by dim reg. So this is, in many limits, you'll see contributions that scale like ddp over p to the d, which diverge in every dimension. The resolution is almost always to use a hard cutoff, because that's the only thing that's guaranteed to work. But then one encounters strange situations like the following. So we might have some integrand that appears to fall off, like many powers of the scale factor. But when we put the hard cutoff, if we take that hard cutoff to be, let's say, the horizon, then this naively suppressed integrand can potentially give rise to an effect that grows with time. And this difference between the behavior of the time behavior of the integrands and the possibility of a large effect that grows with time is essentially the source of a lot of confusion around the late time behavior of Superhorizon modes. But really, at some basic level, the problem is that we're including hard modes in these calculations. So when we did that loop calculation, the dangerous piece of that calculation is the mode whose energy is parametrically the same as the cutoff, h. Now, in a proper EFT, we know that those hard modes should only be changing coefficients in the effective action. And even better, if our EFT makes power counting manifest in the way we calculate loops, when we see a loop integrand like d3p times p, we should get an answer after regulating it in a way that respects power counting that scales like the soft momentum k over ah to the fourth. So our goal for the rest of the talk is to construct an EFT with these properties. So what we're the conceptual picture we should have in mind is that we're looking for some way to describe only the wavelengths who are parametrically large compared to the horizon. This will be often useful to think in comoving coordinates, so that the k, the wave number, is fixed under time evolution, and it's the horizon, comoving horizon that's shrinking, so that k over ah is much less than 1, describes the late time behavior of this mode. Now, the first step to constructing an EFT is to identify what the soft degrees of freedom are. And so the easiest way to do that is just to take the free scalar field as an example and look at what the solutions do in this long wavelength limit. So as you all know, you take a massive scalar field and take the k to 0 limit, you'll find two solutions that scale like power laws in A. So the growing mode, as we'll call it, scales like the soft, decays the most slowly outside the horizon. So it scales like a power alpha, which is the smaller of the two coefficients. And there's the decaying mode, which scales like to a to the negative power beta, where beta is a larger number. Alpha plus beta is fixed to be equal to 3. Or alternatively, we can write it in terms of this new parameter, which depends on the mass. Now, the strategy for this effective theory is, instead of expanding the field around 0, we're going to think of expanding the field around these classical long wavelength solutions. So we can think of this from the top down as being an ansatz where we factor out the classical, this long wavelength behavior. So we're going to factor out the powers of the inverse co-moving horizon, ah to the minus alpha or ah to the minus beta, and then the fields phi plus and phi minus describe fluctuations around those solutions. This strategy is similar to other effective theories like heavy quark effective theory. And we'll see that some of those properties appear as we go along. This way of constructing the effective theory then has the nice feature that phi plus and phi minus are like scaling operators. So we can think of them as carrying dimensions of the long co-moving momentum k to the alpha or k to the beta. Of course, in addition, we're going to have the hard modes, which we integrate out to get, and one can show that this procedure of integrating out the hard modes gives rise to a local effective theory for the phi plus and phi minus. Now, if we take a free action and we just plug in this ansatz, we'll arrive at the following action after a number of fielder definitions. So the key thing to notice here is that we arrive at a first order kinetic term. So we only have a single time derivative in our kinetic term, and then we have a second order gradient term. This is such that the leading equations of motion, the 0th order gradients, are just that phi plus and phi minus are constants. And this should make sense because we factored out the behavior in long wavelengths, so that those pieces would have been the constants in the long wavelength solutions. And at subleading order, we find gradient corrections. Now, the fact that it's first order also matches our degrees of freedom because we started with a single field with two propagating modes. Now we introduce two fields to characterize those modes, so we have a first order action so that we didn't introduce any additional degrees of freedom. Now, from this first order action, we can see that the phi plus and phi minus are actually conjugate momenta of each other, which means that they'll have the usual commutation relation for the canonical, they'll have for the conjugate momenta, but now it's between the phi plus field and the phi minus field. So in addition to the fields, one of the unusual things about this effective theory is that we also have to introduce initial conditions. Because we're following the modes after they cross the horizon, we need to describe their behavior at horizon crossing. The easiest way to do that is just to take the full solution and expand it in a long wavelength limit to read off the normalization of these modes. So in particular, if we take the usual construction in terms of creation and annihilation operators, one's led to find that the phi plus and phi minus fields actually have classical statistical fluctuations where the power spectra for these fields follows the dimensions, where phi plus or phi minus scale is k to the alpha and k to the beta, with order 1 coefficients c and d. In addition, they have the canonical commutator, but these are classical correlators that are consistent with the fact that phi plus commutes with itself and phi minus commutes with itself. Okay, so that was how we get to this effective theory from the top down. Of course, any good effective field theory, being a consistent description of a set of scales, should be completely derivable without appealing to physics outside of those scales. So in particular, if you give me the propagating degrees of freedom, the symmetries, and the initial conditions, I should be able to construct the full theory. So we've already identified the fields. So what are the symmetries? So the first is the trivial scaling symmetry. This is true of any FRW. If you take the metric and write it in the usual FRW form and just rescale the coordinates and rescale the scale factor, you arrive at the same metric. Now, normally this doesn't act in any interesting way on the fields themselves, but because of this ansatz, now the phi plus and phi minus fields behave like scaling operators under the symmetry. And this is familiar from people who've studied the conformal invariant properties of correlators in de Sitter. And similarly, when we take the full de Sitter space, we will have not just the scaling symmetry, but also the special conformal transformations associated with the de Sitter isometries, where indeed, again, the phi plus and phi minus modes behave like scaling operators of dimension alpha or beta for phi plus and phi minus. Now, those are the obvious symmetries that descend from the UV. One of the novelties of this effective theory is that there are additional symmetries related to the way the field is constructed. So in particular, we've taken one field and decomposed it into many. And as a result, there's actually no unique way to do that. And so there's a residual reparameterization invariance related to the fact that there's more than one way to split these two fields. This RPI symmetry mixes the phi plus and the phi minus field, so the growing and decaying modes. And ultimately that will, when using the symmetry, we'll see that it relates operators with phi pluses to operators with phi minuses. We call this RPI because a very similar symmetry arises in heavy quark effective theory for very similar reasons as one-to-many split. And so by some rough analogy with heavy quark effective theory, you could understand the role of this symmetry. So now having written down the symmetries, we should be able to write down the effective action. So if we only included the scaling symmetry and the translations and rotations of the spatial slices to second order in the fields and second order in derivatives, we would arrive at the following action. So this action has 10 independent couplings and 2 independent scaling dimensions. This should be compared to our top-down description that had one free parameter, alpha, because the alpha and beta were fixed by the combination alpha plus beta equals 3. But okay, we haven't used all our symmetries yet, or all of the freedom in describing the fields. So the first thing one can do is one can show that by a field redefinition, you can always fix alpha plus beta equals 3. So already this fact that alpha plus beta equals 3 is not a property of the UV and not a property of the actually having the solutions, but just a general property of the effective theory. Next, we can use this RPI symmetry. So this RPI symmetry, as I described, relates phi plus and phi minus operators. And as a result, it relates the couplings, making the action invariant under the RPI symmetry, enforces that the couplings associated with phi plus operators and phi minus operators and mixed operators are all the same. So this makes all the mass terms equal, all the gradient terms equal. It makes all the second order time derivative terms equal, but also relates the first order time derivatives to the second order time derivatives. So this reduces us down to 3 free parameters plus the scaling dimension alpha. Next, we can perform another field redefinition, which shifts the difference between alpha and beta and sets n squared equals to 0. So all of this up to step 3 is independent of using the actual isometries of de Sitter. Finally, for a fixed de Sitter background, we can use the de Sitter isometries, which relate space and time. So they relate the spatial gradient terms to the time derivatives, and thus get us back to the one free parameter alpha of the UV description. So by following all of that, we arrive exactly back at the action we had from the top down. So far, I still would have had second order time derivatives and first order time derivatives, but because of the fact this is an effective theory and we need to constrain the number of propagating modes, it's known that what we need to do is to replace higher order time derivatives in the quadratic action using the lower order time derivative equations of motion to prevent additional propagating modes. So when we do this, this second order time derivative is replaced by a fourth order gradient term that we can drop at this order. So keeping only second order gradients, we arrive back at the action we wrote from the beginning. Okay, so having figured out how to write down the quadratic action, we're now ready to move on to writing down all possible interactions of this effective theory. So the first thing you would think to do by power counting is potential like terms. So this would be phi plus to the n, phi minus to the m. Now, remember, phi plus behaves like an operator of scaling dimension alpha, phi minus like an operator of scaling dimension beta. So the dimension of the operator itself is n alpha plus m beta. And then our measure scales like 1 over k cubed. The time part of our measure doesn't scale like anything. And so we now make up the dimensions of this action using the only parameter, the only scale left in the problem, which is the inverse comoving horizon, AH. So if I make up the dimensions, I have some dimensionless coefficient C, and this AH to the power 3 minus n alpha minus n beta. In this way of writing the action, we would expect a correction to scale like k over AH to the n alpha plus m beta minus 3. That's the power counting you would expect given the scaling behavior of this operator. So when this power is negative, that means that this effect grows with time. It grows like a power of AH, so it becomes more important as time goes on. So we'll call that relevant. When this exponent is 0, it means that it's equally important at all times, and so we'll call that marginal. And when this power is positive, it decays with time, and we'll call it irrelevant. So naively, the leading interaction is potentially relevant, and that's for phi plus to the n. It scales like an operator of dimension n alpha, which is potentially less than 3, and thus would correspond to a relevant deformation. But this actually turns out to be wrong because this operator can always be removed by a field redefinition. This actually you would already see in perturbation theory, because if you went to calculate effects with this operator, you would find that it doesn't contribute. So instead, the first thing that can't be removed by a field redefinition is phi plus to the n phi minus. This operator scales like n alpha plus beta, which because alpha plus beta equals 3 is dimension 3 plus n minus 1 times alpha, which is always greater than 3 for alpha greater than 0, and therefore is always irrelevant. So this means up to leading order and gradients, all interactions are irrelevant, and there's a finite number of potential terms that are capable of being more important than the leading gradients. And so the full action up to k squared over a squared suppressed terms is some finite number of potential terms that are irrelevant. In addition, we still have to specify the classical initial conditions that are given here. Again, those arise from matching to the UV. And are again consistent with the scaling behavior the scaling dimensions that we read off from the action. Okay, so now let's apply this first to quantum field theories in fixed de Sitter space. So if we have a massive theory, we have alpha greater than 0. So let's say we take a massive order Hubble or not parametrically small, then alpha is some order 1 number, and we'd expect that it approaches a free theory as we compute loop corrections. So if we can just by brute force calculate fairly straightforwardly in this effective action using what you would expect from a phi-4 theory. So a quartic term, phi plus cubed, phi minus. At one loop, this thing vanishes because it's a dim reg type 0 from the loop integral, and the first non-trivial correction arises at 2 loops, and is suppressed by k over h to the 4 alpha, again consistent with what we would expect from it being irrelevant. Now this doesn't mean that massive theories lack any interesting dynamics. It just pushes the interesting behavior to composite operators. So in particular, we can still get anomalous dimensions for composite operators, like the phi plus squared interaction. So for example, if we go to look at the one loop correction to the phi plus squared 2-point function, one finds something that looks like this familiar d3p over p cubed divergence. Now this divergence is easy to see, but one does immediately encounter the problem that these kinds of divergences are harder to regulate. Now the trick here is in our effective theory, we'll do what we call dynamical dimensional regularization, which is to analytically continue in these parameters alpha. And so by doing so, analytically continuing around alpha equals 1, one can extract for that particular case, the conformal mass is alpha equals 1. It's fairly straightforward to isolate this pole, which includes a logarithmic correction, k over ah. Now, at this point, this looks just like any other effective theory. We've calculated some correction. It has a log in it. We have a UV log divergence, and we should immediately think to apply RG. Now, because the UV scale in this problem depends on time, A times H is a time-dependent quantity, we don't do actual RG, we do what's called dynamical RG. So the regularization scale is now some artificial time that one introduces, and the Callan-Szymanczyk equations arise from demanding that the full answers are independent of this artificial time you've introduced to regulate these large logs. Solving the Callan-Szymanczyk equation, you take this coefficient of the log and you can resum it to get this correction to the scaling behavior, which we've written here like k over ah to the 2 gamma, where gamma behaves like an anomalous dimension. And in fact, because this is the conformal mass, one can check that this is in fact the anomalous dimension you compute for the phi squared operator in flat space. So it's not surprising that one arises at this conclusion. Things get more interesting when you move to light scalars. So when we take alpha to 0, corresponding to taking the mass to 0, we now have an infinite series of interactions that are all becoming marginal. So the phi plus to the n, phi minus are all approaching dimension 3. And also because they're all approaching dimension 3, they're all becoming degenerate. For this reason, you should now think, imagining an RG-like process, that these operators can mix under dynamical RG. This is already easy to see just within the Gaussian theory, where you take a composite operator phi to the n, and you contract any two legs, you'll find something that's increasingly looking like a divergent loop integral, d3p over p cubed to the minus 2 alpha. And as alpha goes to 0, that looks like our usual log divergence. And so in fact, we can extract that log and again, write a Callan-Szymanczyk-like equation where now we have two pieces. So the first term is from the classical time evolution that we get from converting this into an equation for the physical time. And the second term is the one that came from this loop integral from contracting two of the fields that gives us log divergence. And this looks like quantum diffusion. And in fact, this equation can be shown is the same as this equation for this operator mixing is the same as stochastic inflation a la Stravinsky. Now, what's also helpful from this point of view is that you can immediately start to understand the behavior of certain corrections. So first of all, we know there can be no gradient corrections to this formula. because those things are suppressed by powers of A, and they can't correspond to operators of the same dimension that will mix. And so any gradient terms that necessarily come with powers of 1 over A will not mix with these phi to the n operators. Furthermore, many of the corrections you could imagine are actually already absorbed into the parameters of our effective theory. Okay, finally, let's talk about metric fluctuations during inflation. So inflation, as of course know, corresponds to the case where we have some field that's breaking the isometries of de Sitter, usually in terms of a scalar field that's evolving in time. Now this additional degree of freedom that comes from symmetry breaking, we will absorb into the metric in terms of the zeta variable, so that our dynamical degrees of freedom are the scalar fluctuation zeta and the two transverse traceless gravitational waves gamma ij. Now, we can consider this problem for just the transverse traceless modes in a fixed de Sitter, but for the purpose of generality, we'll allow interactions for both gamma, and we can allow interactions that break the linearly realized Lorentz invariance for both zeta and gamma. However, even though this problem has less linearly realized symmetries, the non-linearly realized symmetries are extremely important. So for the scalar modes, it's well known that that we can shift the field and rescale the coordinates to leave the action invariant. And this corresponds to a large diffeomorphism that acts non-linearly on our field zeta. Demanding that this symmetry, which is the symmetry of the UV, that this is also imposing the symmetry in our effective theory has two immediate consequences. First, it tells us that the growing mode, zeta plus, has to have alpha equals 0. That's the only allowed value of alpha that's consistent with this nonlinear shift. Second, this nonlinear shift, this invariance under this shift, also enforces that interactions come with derivatives. So there's at least two derivatives acting on any of the zeta fields. There's a more complicated non-linearly realized symmetry for the transverse traceless fluctuations, but the moral is still the same. It's a non-linearly realized symmetry, which arises from a large diffeomorphism, and ensuring that this is a symmetry forces that the growing mode has alpha equals 0, and the interactions are derivatively suppressed. As a consequence, we can write down the effective theory for these modes very easily. We know that essentially we have the first order kinetic terms plus terms that are necessarily suppressed by at least AH squared due to the derivative nature of the couplings. Now, this is where the power of the effective theory calculations work. The way in which we regulate our loops preserves power counting. And so when we see that all the corrections are suppressed by powers of AH, we're guaranteed that if we do loop corrections in this theory, that all of the loop corrections to the leading behavior are also suppressed by powers of K over AH at least squared and higher orders. And this is all that is needed to get the conservation of zeta. So the leading behavior is just tells us that zeta dot and gamma dot are 0 as operators, and that loop corrections only fall off like increasingly high powers of the soft momenta over the comoving horizon. Now this is morally similar to some of the previous arguments. One can still use the symmetries to arrive at an operator-like equation where the operators on the right-hand side are derivatively suppressed. But the key here is that what the effective theory has done is that it's translated the suppression of the operators by powers of AH into a manifest statement about loop corrections, just because the power counting is now preserved along with the symmetries. Okay, just to wrap up, so what we've shown here is how to construct the soft de Sitter effective theory, which is a theory for the long wavelength degrees of freedom in de Sitter. When considering massive quantum fields in a fixed de Sitter background, all interactions in this effective theory are irrelevant. So the leading behavior of correlators is fixed at horizon crossing and not affected by evolution on superhorizon scales. When the quantum field theories are massless, some interactions become marginal and operators can mix, and the dynamical renormalization group associated with those marginal operators is equivalent to the stochastic inflation framework. When we consider metric fluctuations in de Sitter or in inflation, one finds that the interactions are always suppressed by derivatives and significantly are higher dimension operators and are always irrelevant by power counting. As a result, all orders conservation of zeta and gamma, so both the adiabatic mode and the transverse traceless mode, is now simply a statement about power counting in the effective theory. Okay, thank you.